big data, security course, or storage, Boolean, and artificial intelligence. So you can take this certification. To access to these courses, you can directly click from here. So I'm doing the example with HCIA course. So actually I am already logged in, but I will sign out because actually the first time that you access to this training, you have to register on the Huawei website to follow the MOOC course. From this website, you can take information about the course. So you will see which are the target trainings, which are the objective of the course, and also the duration of the course and the trainer for the course. If you go on course outline, you will see the details about the topics which are covered in HCIA 5G. So topics are motivation and industry progress. In here you will find information about the driving force of 5G evolution, the protocol standardization for the 5G network, industry chain and ecosystem, and global commercial deployment plan. The second chapter is about the network architecture and key technology. And in here you will find information about business scenarios and key capabilities and the new network architecture and key technologies for 5G network. Actually, this is the topic that we are going to cover today. Then the third chapter is about some use cases. So in this chapter, you will find information about the 5G business value and development and the business application and cases. And then there is the last chapter, which is the typical industry application solution of 5G. And in here, you will find the description of some very typical industry application like Internet of Vehicles, smart healthcare solution, smart education, and smart grid. At the end of each chapter, by following this MOOC, you have the possibility to take a quiz. This quiz is not the certification exam and it's not the pre-test. This test is just for yourself to test your competencies. And so also the final exam. This final exam that you will find inside the MOOC course is not the certification exam and it is not the pre-test. This is just for you to test yourself. So to enroll to this course, you can click on enroll now. And if you are not registered to the Huawei website, you have to register. So you click on register and you put some few information actually, like the user ID. You can choose your user ID. You can input your email password, your name, your country, and if you want, you can also input your phone number. Then you insert the code in the image, and after agree with Huawei terms and condition and the privacy policy, you can register yourself. So actually, I am already registered, so I will log in with my account. After you register, you can log in and view the course. If you click on View Course, the page relative to the course will be displayed. So from here, you can follow the MOOC course and take the final exam, which I remind you is not the certification exam nor the pre-test. This is just for you. So from here, you can follow the streaming and learn about new topics. So this is about the first step. Then the second step is the exam preparation webinars. In this moment, you have three available webinars, which are routing and switching, Boolean, and 5G. Each webinar is arranged in 4 sessions. The first session is about the course overview. For HCIA 5G, we already had this session on last week. Then the second session and the third session are related to some specific topics. For example, today, 21st of July, we are going to address the 5G network architecture and key technologies. So from here, you can access to the webinar. Then on 7th of August, we will have another session in which we will talk about 5G industry application and solution. And then we will have the last session, which is a summary of the entire program. And then we will see some example of exam questions. During the webinars, we kindly remind you to keep your microphone on mute. And if you have any question, you can write your question on the chat or on the question and answer window. Then we will collect all of your questions and we will create an FAQ area with all the answers. And the FAQ area will be available on this web page. So if today you have any question, you can write your question on the question and answer window. Then at the end of the training, and at the end of the webinar, we will collect all of your questions, we will provide an answer, and then we will upload the FAQ with the answer on this website. The step 3 is the pre-test. So to have the possibility to book your certification exam, you have to pass the pre-test with a score of 60 points among 100. You can take the pre-test from here. So for example, for HCIA 5G, you can click here on Start Pre-test and you can take your pre-test. After you pass your pre-test, you can click on here in Apply for voucher. And applying for the voucher, you can get all the information to take the certification exam. So from here, I'm going to show you, apply for the exam, and you will input your name, your account ID, your email, your contact number. You will select your country and your organization type. You will select the pre-test that you already passed, and then you can submit the request. After you submit the request, you will receive information to book your certification exam. The booking of certification exam is the step 4. So from here, you can see the deadline date to book your certification exam. And here you have information about the certification exam. To book the certification exam, you need the authorization code and the voucher code. This is valid for all the exam except the HCIA 5G. For the HCIA 5G, after you apply for the voucher, you will receive an email with the indication to book your HCIA 5G certification exam. You can find all the information in here. In here you can use the exam voucher to book any listed HCIA exam except HCIA 5G. HCIA 5G does not require the voucher code. You will be contacted by email to make the arrangement for the exam. You still have to apply for the voucher, but after you apply for the voucher, you will receive an email with instruction to book the certification exam. For all the other certification exam, you will receive the voucher code and you will use it together with the authorization code to book the exam from here, from Book Exam link. If you have any question related to the organization or to the exam, you can write an email to uktraining@huawei.com. This email address. I just remind you, you can take your exam from home, but you will take the exam through a platform, so you will be viewed through the webcam. And during the exam, it is not possible to use external tools like mobile phone, for example, or some notes. it is not possible to use them. So during the exam, you should be only focused on the exam. You are not allowed also to change your screen during the exam. Okay. So after this introduction about the program, I think we can start with the two-day topic. So I'm going to share again my screen so we can see the two-day topic. So here we are. So today we are going to discuss about the 5G network architecture and key technologies. So in this course, we will discuss about the key capability of the 5G network, and basing on these capabilities, we are going to understand which are the changes in 5G network architecture and their interface with respect to preceding technologies, and which are the new technologies that are introduced to meet the capabilities of the 5G network. So these topics is arranged in two chapters. The first chapter is about business scenario and key capabilities. And the second chapter is about the 5G network architecture and key technology. So we are going to start with the business scenarios and key capabilities. During the first session, we already discussed about the ITU vision of 5G network. In here, IMT 2020 is the formal name of our 5G. The ITU in 2015 defined the formal name of 5G as IMT 2020 and also defined three application scenarios on which vendors, operators, and companies based to make some researches about the 5G network. These three scenarios are enhanced mobile broadband, ultra-reliable low-latency communication, and massive machine-type communication. Usually, these three application scenarios are represented at the vertex of a triangle. This has actually a meaning because with this representation, the focus is on the difference about in the network requirement that all of these three scenarios require. So in particular, if we talk about enhanced mobile broadband application, inside this application scenario, we will find all the application that requires a very high bandwidth and very high throughput. A throughput that can reach 10 or also actually 20 gigabit per second. So in here, we will find applications such as the virtual reality, augmented reality, or for example, video streaming in very high definition. On the second vertex, we will find ultra-reliable, low-latency communication. In here, we will find application which requires ultra-reliability and ultra-low latency. When we talk about ultra-reliability, we are talking about a reliability of 99.999%. This means that in 1 year of operational working of our network, the network will be out of service for less than 5 minutes in 1 year. And when we talk about low latency, we are talking about a latency as low as 1 millisecond end to end. So here we can make a note. When we talk about 1 millisecond of latency end to end, first of all, we are talking about the user plane latency, not the latency related to the control plane. So 1 millisecond is for the user plane. And when we talk about end to end, we are referring to the application, to the user equipment side, to the application layer, to the core network. So 1 millisecond end-to-end means 1 millisecond of latency on the user plane from the user equipment to the core network. So in here we can find applications such as the Internet of Vehicle or the remote surgery. These are kind of applications for which we require very high reliability and a very low latency, because information needs to be received and processed with a very low latency to make this application work. On another vertex, we have the massive machine type communication. As the name suggests, is the communication between machine, but in a massive way. So basically today, with the technology that we already have, we are talking about Internet of Things, IoT. With technologies that we have up to now, like for example, the narrowband IoT, we are able to reach 10,000 of connection per square kilometer. But the trend for the future is that the number of connection between devices is going to increase exponentially. So with massive machine type communication in the 5G network, we will be able to reach 1 million connection per square kilometer. So for massive machine type communication, we basically don't have requirement in terms of bandwidth, and we don't have requirement in terms of latency or in terms of reliability. We just have requirement in terms of number of devices that can be connected and in coverage. Because of course, all the devices need to be covered by a radio network. So this is the reason why these three application scenarios are represented at the vertex of a triangle to underline the difference in terms of network requirements. So for enhanced mobile broadband, we require a broad bandwidth. For ultra-reliable low latency communication, we require high reliability and low latency. And for massive machine type communication, we require wide coverage and high number of connection per square kilometer. The target of the 5G network is to be able to provide all of these three application scenarios by using one single network. So we can already anticipate that one of the key technology is the network slicing. Network slicing means that we have one single physical network, but we can divide our single physical network into many logical portions of our network. Each portion, each slice, contains the resources to make one application work. And the network slicing concept, it is actually an end-to-end concept. So we have network slicing at the radio layer, we have network slicing at transport layer, and we have network slicing at core layer. So it is an end-to-end concept. So if we look at the picture that we can see in the right of this slide, we can see a comparison between comparison of key performances between the 5G and the 4G network. And we can see, starting from the peak rate, with 5G, we are able to reach 10 gigabit per second of peak rate. So in this image, basically the yellow part is the 5G, while the orange part is the 4G KPI. So for the peak rate, 5G, you can see from here, can reach 10 gigabit per second of peak rate, actually also 20 gigabit per second in downlink. While the 5G allow us to reach 1 gigabit per second. From the user experience rate, with 5G, we can reach 100 megabit per second. And with 5G, the spectral efficiency is increased by 3 times with respect to the 4G. Also, the mobility is increased up to 500 kilometers per hour. And we already talked about the delay. We can reach a delay of 1 millisecond, which is actually from 30 to 50 times more with respect to the 4G network, because with 4G network, we can have latency of 30 or 50 milliseconds. Also for the connection density, we already said with 4G, we are able to reach 10,000 of connected devices per square kilometer, while with the 5G we're able to reach 1 million connected devices per square kilometer. And also for power consumption, we enhanced the power consumption by 100 times with respect to 4G. So this is a comparison about the key performance indicator between 3G and 4G and 5G network. So we'll see from here the important performance to reach our 1 millisecond of end-to-end delay, 10 gigabit per second of throughput, 1 million connection per square kilometer, and 500 kilometers per hour of speed. And we have the concept of network slicing, as we already discussed. So to reach these performances, we need a new architecture and a new air interface. So today we are going to talk about this new architecture and new air interface. On the new architecture, actually, we are going to see that we have different options to build up our 5G network. And also we are going to see which are the new technology which is introduced in the air interface to reach a higher throughput and higher frequency efficiency, a lower latency, and a stronger coverage. So we can start with the new architecture. Talking about the new architecture, we actually have two scenarios of architecture in our 5G network. One architecture is called non-standalone network, and the other one is the standalone network. So we are going to describe which are the differences between the non-standalone networking and the standalone networking. Actually, to do this, I'm going to use the whiteboard so we can make some example. So I'm going to change my screen so we can use the whiteboard. So let's start with the concept of non-standalone networking. What does mean non-standalone networking? Non-standalone, as the name suggests, means that our 5G network can't work alone. So our 5G network needs the 4G network to be able to provide services. For non-standalone network, we actually have different options. So we can divide the non-standalone option in option 3 series, so a family of options actually. Option 3 series. Then we have option 7 series. And we have also option 4. While for standalone, the real standalone 5G network is the option 2. So we are going to describe this option and we are going to see the difference between them. Actually, option 3 series is a family of options. So in here we can find option 3, option 3A, and option 3X. Same thing for option 7. With option 7 family, option 7 series, we will find option 7, option 7A, and option 7X. And for option 4 series, we will find option 4 and option 4A. So we start from here, from the non-standalone networking with option 3 series. Starting from option 3. Actually, in the option 3 series, let's say the structure is the same for option 3, option 3A, and also option 3X. So in option 3 series, we have the 4G base station, so what we call E node B. We have the 5G base station, that is the G node B. And the core network is the 4G core network. So in option 3 series, we are going to use the evolved packet core network, the 4G core network. So this actually is the same for all the 3 options. So for option 3, option 3A, and option 3X. So we have E node B, G node B, and 4G core network, EPC. This is what it is in common between our 3 options inside the family of option 3. So our user equipment in all of these 3 options can communicate with both G node B and E node B. So can communicate with the 5G and also with the 4G core network at the same time. This characteristics, this feature is called DC, dual connectivity. So the dual connectivity is the possibility, the capability of our terminal, of our user equipment to communicate with both the 4G network and the 5G network. So actually, the user equipment can communicate with the E node B, so with the 4G network, to exchange both information of user plane and also control plane. So I'm going to represent with the continuous line the user plane and with the dashed line the control plane. While the user equipment can communicate with the G node B only for the user plane. So in this option, it is the E node B which is responsible for the control plane. So it is the E node B which will exchange control plane information with the core network. And actually in option 3, it is also the E node B which exchanges the user plane with the core network. Then the G node B will receive control information and also the user plane from the E node B, so from the 4G side. So we can see from here that our master node is the E node B, is the 4G base station. So in this option, what is called the anchoring point, the data split point, is the E node B. That means that all the user plane is converted to the E node B, and then the E node B will split the user plane to deliver the user plane to the G node B. So this is option 3. What is different in option 3A? From the communication between the user equipment and the network, we have exactly the same situation. So our user equipment can communicate with the E node B to exchange both user plane and also control plane, while it can communicate with the G node B only to exchange user plane. Then, even in this case, it is the E node B which is responsible to exchange control plane with the core network. But the user plane can be delivered to both directly, to the E node B or to the G node B. So in this option, we have a direct connection between the G node B and the core network for the user plane. And as before, actually, G node B and E node B can communicate each other to exchange information for both user plane and also control plane. In here, our data split point is the core network. So it is the core network with which will split the traffic and send some traffic to the E node B and some traffic to the G node B. This option is actually seldom used option because it is not so efficient as an option, because the data split is performed at the core network, but the core network is not aware about the radio condition. So the split will be performed without knowing actually about, for example, the load on the 5G or 4G side. So actually this option is very seldom used, and to be honest, Huawei does not support this option. Then we have option 3X. Actually, option 3X is the most used option worldwide. In this option, again, the user equipment can communicate with the eNode bit for both control plane and user plane, and can communicate with the GNode bit only for the user plane information. Then again, the eNode bit can communicate with the core network for both control plane and also user plane. And again, in this case, we have a direct connection for the user plane between the core network and the 5G base station. And again, in this case, 4G and 5G base stations can exchange information each other for both control plane and user plane. So, which is the difference here? Here, the data split point is on our GNode bit, is on 5G side. So, what we are going to have is that the traffic is managed by the GNode bit. Then the GNode bit will split the traffic to the eNode bit if needed. So this is the option 3 family, composed by option 3, option 3A, and option 3X. The structure, let's say, is the same. So in all of the 3 cases, we have our user equipment in dual connectivity. That means it can communicate with 5G or 4G base station at the same time. And in all the 3 options, we have the 4G core network. What changes between these 3 options is the anchoring point, the data split point. But since the control plane is managed by the eNode B, we will call the eNode B as the master node, while the GNode B is recognized as the secondary node. So this is option 3 series, the family of option 3. As I said, Huawei does not support option 3A because it is not so efficient. If we talk about option 7, now we change color to be compliant. If we talk about option 7 series, it is very similar to option 3 series, but instead of having the 4G core network, we will have the 5G core network. So if we talk about option 7 or option 7A or option 7X, we will have more or less the same structure, but instead of having the evolved packet core, we will have the next generation core, which is the 5G core network. We are going to discuss about the 5G core network in a while. So the rest is exactly the same. So even in option 7, our user equipment can communicate with both eNode B and GNode B. And the control plane is managed by the eNode B. So the eNode B will remain the master node, and the GNode B will remain the secondary node. In option 7, the data split point is still the eNode B. In option 7A, the anchoring point, the data split point, is still the core network, the 5G core network, while in option 7X, the data split point is the GNode B. And actually, in option 7, we are talking about enhanced eNode B. Why we're talking about enhanced eNode B? Because we have to upgrade our eNode B to give to the eNode B the opportunity to talk with the new core network, which is the 5G core network. So our 4G base station need to be upgraded to be capable to communicate with the next generation core, with the new core network. So these are option 3 and option 7 series. So we also talked about option 4, and we said we have option 4 and option 4A. So we are going to see which is the structure of option 4. In option 4, we have option 4 and option 4A. We basically, even in this case, we have our eNode B and we have our gNode B. In option 4, the core network is the 5G core network, that is the next generation core. So in both the options, eNode B, gNode B, and the next generation core. Even in this case, our user equipment, it is in dual connectivity, but this time in option 4, the control plane is managed by the gNode B. So in this case, user equipment can exchange control plane and user plane with the gNode B, and can exchange the user plane only with the eNode B. Then the eNode B can exchange user plane and control plane with the gNode B, and the gNode B is responsible for exchanging both user plane and control plane with the 5G core network. So in here, the data split point is our gNode B. And even in this case, actually, the eNode B is the enhanced eNode B. While in option 4A, again, our user equipment can exchange both control plane and user plane with the gNode B. It can exchange only user plane with the eNode B, then both eNode B and gNode B can communicate with the core network. And again, we have the communication between eNode B and gNode B. And here, the data split point is the core network. So these are our non-standalone options. If we are talking about interfaces, interfaces for the non-standalone network are almost the same of the 4G interfaces. Actually, I think I'm going to use another page, so we will be more clear. So let's see, option 3 series. Let's take in consideration option 3X, which is the most used one. We said we have our EPC, we have 4G base station, which is the eNode B, and we have our 5G base station, which is the gNode B, and we have our user equipment. And for option 3X, we said user equipment can exchange both I made a mistake. User equipment can exchange only user plane with the gNode B, and can exchange both user plane and control plane with the eNode B. Then both eNode B and gNode B can communicate with the core network for the user plane, but only the eNode B is responsible for the control plane. And then eNode B and gNode B can communicate each other. So if we talk about interfaces, which are the interfaces? The interface between the user equipment and the base station is still the UU interface, the air interface. Then the interface between our base stations and the core network is the S1 interface. But from the E node B side, we have S1 for both control plane and user plane. And on the 5G side, on the G node B side, we will have S1 interface, but only for the user plane. The interface to allow E node B and G node B to communicate each other is the X2 interface for both user plane and also control plane. This is for option 3 family. If we look at the option 7, so like for example, option 7X, we said the structure is basically the same, but we have the 5G core network, which is the next generation core. We have our user equipment exchange user plane with the G node B and both user plane and control plane with the E node B. Then the E node B can communicate for both user plane and control plane with the core network. The core network and the G node B can communicate only for user plane, and E node B and G node B can communicate each other for both user plane and control plane. In this case, the air interface remains the UU interface. And also the interface to allow E node B and G node B to communicate each other is still the X2, both user plane and control plane. But the interface to communicate with the 5G network is a new interface. It is called NG interface. NG stands for next generation interface. So this NG interface from the G node B side is only for user plane, and from the E node B side is NG for both user plane and control plane. So whenever we have the 5G core network, the interface between our base station and the core network, it is the new generation interface, the next generation interface, which is called NG. So these are the non-standalone options. And as you can see from here, we always have the E node B that helps our 5G network to provide services. The final target is to reach the standalone network. In the standalone network, the 5G network is completely independent from the 4G network. So we will have our 5G base station, we will have our 5G core network, next generation core, and we will have our user equipment that can communicate with our G node B for both user plane and control plane. And our G node B can communicate with the core network for both user plane and control plane. And of course, different G node Bs can directly communicate each other for both user plane and also control plane. So in this case, if we talk about interfaces, the air interface is still the UU interface. The communication interface between the G node B and the next generation core is again our next generation interface, our NG interface for both user plane and control plane. While the interface that allows two G node Bs to communicate each other, it is called XN interface for both user plane and control plane. So we are starting from 4G network to reach the 5G standalone solution. So starting from the 4G network, we can have different steps. For example, these are just examples, but for example, we can start from G, then introduce the 5G radio and use, for example, the option 3X. Then we can introduce the 5G core network and move to the option 7X, and then we can remove the 4G dependency and reach the option 2. This is option 2. Or, for example, we can start with option 3x, then move to option 7x, and then have another step. So move, for example, to option 4 and then to option 2. So actually, the evolution to the 5G standalone will be a smooth evolution. We will have some intermediate step before to reach the option 2, which is the standalone solution. So this is the overview about the different options that we may have. I'm going to share again the slide so we can see the reference on the slide. So here we are. So here, as you can see, actually, it is basically represented the option 3x. Can you recognize that? We have the 4G base station, LTE. We have the 5G new radio. And we have the 4G core network. And the anchoring point in here is the G node B. So the data split point is the G node B. With this kind of architecture, we only support enhanced mobile broadband services. Why this? This because to support other services like the ultra-reliable low-latency communication services, we need the 5G core network. And we are also going to understand why we need the 5G core network to support the ultra-reliable low-latency communication services. But with the option 3 family, we can only support the enhanced mobile broadband. So in this moment, actually, we are providing only enhanced mobile broadband services, which are defined in the release 15 of the 3GPP protocol standardization, which is already frozen. I remind you, when a release is frozen, that means that no more modification will be accomplished to the release, so we can start the commercial deployment of the network. Ultra-reliable low-latency communication services are defined in release 16, which is not frozen yet. So at this moment, we cannot commercially provide ultra-reliable low-latency communication services because the release which defines this kind of services is not frozen yet. And moreover, to provide this kind of services, we need the 5G core network. So in here, it is also said that in this case, in option 3x, the LTE is the anchor point. That means it's the LTE which is responsible for the control plane. So this is called data split point. While the anchoring point, which is the master node, it is the LTE side. It is the E node B. And also, the 5G in the non-standalone scenario is not open, is not able to provide a continuous coverage. We can see from the picture, actually we will better discuss later, but with 5G we are using basically higher frequencies, and you know that our higher frequencies means lower coverage. So if we are in a non-standalone scenario, the coverage of 5G is lower than the coverage of LTE. So it is not able to provide a continuous coverage when we have non-standalone architecture. Then, from the right side picture, we can see the standalone solution. In the standalone solution, you can see from here, actually the 5G network is independent from the 4G network. And this kind of architecture supports enhanced mobile broadband services. It supports ultra-reliable, low-latency communication services and massive machine type communication. We need the 5G core network, and we have high requirement for continuous network because now it is an independent network. So we cannot rely upon the 4G network to provide coverage. If we have an independent 5G network, then we need to have a continuous coverage. So here we have the overview about also the interfaces. So this is the standalone networking. So as we said, the communication between different communication is accomplished through the EXN interface, while the communication between the base station and the core network is accomplished among the NG interface. So in here, you can see, for example, these two entities, AMF and UPF. We are going to describe them, but AMF stands for Access and Mobility Function, and UPF stands for User Plane Function. Basically, the AMS is node of the 5G core network, which correspond to the MME in 4G core network, while the UPF is the node of the 5G core network, which correspond to the serving gateway in the 5G core network, in the 4G core network. So the radio part of the 5G, it is called NR, new radio, while the core network, it is called next generation core. So let us see now the differences between the next generation core and the evolved packet core. So here you have a table in which you can see that actually the first thing that we can notice is that every node of the 5G core network has this half as a final part of the name. So AMF, I said, it stands for Access and Mobility Function. AUSF stands for Authentication Server Function. SMF stands for Session Management Function. UPF stands for User Plane Function. And PCF stands for Policy Control Function. So you can see all the nodes of the 5G core network are called functions. Why that? Because the 5G core network, it is a cloudified network. It is divided, it is arranged in network function services. That means for 5G core network, we are not going to have a specific hardware with specific functionalities. Everything is virtualized. So we will have servers. In these servers, we will have virtual machines, and these virtual machines will emulate the functions of the nodes of the 5G core network. So that's why we are talking about function. The 5G core network born virtualized and cloudified. So we will move far from the concept of central office. We are going through the concept of data centers. We will have data centers. In these data centers, we will have servers. And in these servers, we will have virtual machines emulating the function of the nodes of our core network. So this is the first difference that we can see with respect to the 4G core network. Another difference, as you can see, in the 4G core network, we have some overlapped function. Like, for example, the MME is responsible for the mobility management. It is responsible for user authentication and for a part of the session management. While in 5G core network, we can see that the AMF is responsible only for mobility management. The authentication server, it is responsible only for user authentication. In 4G network, the session management is in charge of the enemy and also of the P gateway, of the PDN gateway. While in 5G core network, we have the session management function, which is responsible for the session management. And also for the user plane data forwarding. In the 4G core network, we have again an overlapped function. This is in charge of the P gateway and also of the serving gateway. While in 5G core network, we only have one entity, which is the user plane function, which is only responsible for the user plane data forwarding. So this is another difference. Each function, each node perform one management. We have no more overlapped functions. Each node of the 5G core network has its own specific function. So we can make another comparison by using the whiteboard. So I'm going to share again the whiteboard. So we can see the differences between also the structure of the 4G core network and the 5G core network. So in the 4G core network, which is the EPC, we have a structure like this one. We have our user equipment that communicates through the air interface with the eNode B. Then the eNode B exchange control information with the NME. The NME communicate with the HSS. And the MME also communicate with the serving gateway. But the serving gateway also communicate with the eNode B. And the serving gateway exchange user plane and control plane with a PDN gateway. The PDN gateway exchange control information with the PCRF for the policy control function. But the PCRF has to communicate also with the serving gateway and also with the HSS. So this is the basic structure of our 4G core network. And from here we can see, for example, here we have the data forwarding. So serving gateway and PDN gateway are responsible for data forwarding. Then we also have MME together with the serving gateway, actually, are responsible for mobility management and session management. So mobility and session management. While, for example, PCRF and P gateway are responsible for service control. And I will use another color, MME together with PCRF and also the HSS are responsible for authentication and for data management. So we can see from here we have some overlapped function. So this is the structure of the 4G core network. So which are the differences with the 5G core network? We are going also to describe the structure of the 5G core network, which is the next generation core. In the next generation core, we have our user equipment which communicates with the radio access network. So here we have actually our G node B. It communicates through the air interface. Then the user equipment can also communicate with the AMF. And the AMF, of course, communicate with the G node B, with the radio access network. For the user plane, the G node B directly communicate with the user plane function. But for the control plane, for all the control part, the centering point is the AMF. So basically, the AMF, we have here like a bus communication. So the AMF is connected to this bus, and to this bus, we can also find all the other functions of our core network. So we will find the authentication server function. We will find the session management function, SMF. Actually, the SMF also communicates with the user plane. Then in here, we find, for example, the policy control function. We will find the UDM. We are going to define all of these entities one by one. And also, we will find some new nodes, like, for example, the NSSF, and also the NRF. So these two are actually new on 5G core network. So, as I said, the AMF is the access mobility function. The access and mobility function is in charge for registration, connection, and mobility management, and it corresponds to the AMME in the 4G core network. Then we have the SMF. SMF stands for Session Mobility Function. So it is in charge for session management, tunnel maintenance, IP address allocation, user plane function selection. So we can select the user plane function. And it is also in charge for quality of service control and so on. So actually, the session management function performs some operations and management that in the 4G core network were in charge of the MME, but also of the serving gateway and also of the PDN gateway. Then we have the authentication server, the AUSF, which is in charge of authenticating the 3GPP and non-3GPP access. So it performs some function that in the 4G connector were performed by the MME and the HSS. Then we have the policy control function, which corresponds to the PCRF of the 4G core network. Then we have the UDM. UDM stands for Unified Data Management. This is the function, the node, in charge for subscriber identification and access authorization. So it performs basically functions that in the 4G core network were performed by the HSS. And then we said we have two new nodes. We have the NSSF, which is the network slice selection function to select. We have the new concept of network slices. So the network slices need to be selected. So this node is in charge to select the right network slicing based on the user equipment request in terms of services. And then we have the network repository function. The network repository function, discovery function for all the functions in the 5G core network. So also this one is a new node. From here, from this structure, we can see that actually we have a separation between the user plane and the control plane. Because we can see the control plane is in here, and this is the user plane. So we have a separation, a real separation between control plane function and user plane function. And all of these nodes, all of the control plane functions can communicate each other. And this communication interface that we represented as a bus, it is compliant to the Internet protocol. So this is the new structure for the next generation core, for the 5G core network. So we can see that it is a service-oriented core network architecture. It can support all access modes, so it can support 2, 3G, 4G, and 5G. It can support also Wi-Fi, narrowband IoT, fixed access, and unlicensed. And it also supports all services. The 5G core network can support voice communication, it can support video services, it can support services related to smart city, that means massive machine type services. It can support ultra reliable low latency communication services and enhanced mobile broadband services. It is flexible because it is virtualized, and it is programmable, again, for the same reason. It is virtualized, so if we need more resources, we can add new virtual machines on a server and make this virtual machine emulate the function of one node of the core network. So it is programmable. If we need less resources, we can use less resources. And it can allow smart pipe. That means it can allow slicing. And also, we have the control user plane separation. We have a service-based architecture, as we already said. We have the concept of network slicing, and it is a native cloud core network. So here we have also a picture that explains us better why network slicing is required in 5G. So in the upper part of the slide, we actually have the 4G network. In the 4G network, we don't use the network slicing. So let us suppose with the 4G core network, we have 3 different kinds of services. We have the standard services like voice, internet access. So we have services related to the mobile broadband. Then let us suppose we have the Internet of Vehicle, which require low latency and high reliability. And let us suppose we have some narrowband IoT application, and we are using one single network. Actually, in this way, without using network slicing, we are not able to differentiate in a so hard way these services. So all of these 3 devices, that is our mobile phone or the car, the vehicle for automatic driving, or for example, our smart meter will basically use the same resources and the same network. So actually, in this way, we are not able to differentiate services. But with 5G and the network slicing, let us suppose we have the same 3 kinds of service. So we have voice and internet access, we have automatic driving, and we have smart meter. We are able, with by using 3 different slides, one slice for each kind of service, we are able to really differentiate these 3 kinds of services. Like each service has its own logical network. So each service has its own resources to be used to provide that specific service. So we are still using one single physical network, but we have different portions. So actually these 3 services are really differentiated each other. So for example, voice and internet access, we will allocate resources for having broad bandwidth. For automatic driving, actually we don't need bandwidth. So our vehicle will have resources that provide low latency and high reliability. While the smart meter will have no resources to enhance the bandwidth, it will not have resources to reduce the latency, it will have resources to connect to different devices. Actually, the control and user plane separation is an important feature because it helps us to increase the user experience and to increase the network efficiency. And with the control plane and user plane separation, this is actually an enable features to have what is called MAC. We are going to describe the MAC. MAC stands for Multi-Access Edge Computing. I'm going to write here, Multi-Access Edge Computing. With the multi-access edge computing, basically, we are able to move closer to the access network. We can move the user plane function, so we can move the core network. We can move the content that we need closer to our access network, and we can also move the computational part closer to the access network. Actually, why control and user plane separation? It is an important feature. We talked about basically the lower latency. And we said 1 millisecond of latency end-to-end means that we have 1 millisecond of latency on the user plane between our terminal and the core network. So why it is important control and user plane separation? Because we can move the user plane function closer to the access. And we can move only the user plane function because we need the low latency on the user plane. So it is not necessary to move all the function of the core network closer to the access. We need to move only the user plane function. And with this separation and with the cloudification of the 5G core network, we can do it. We can implement the user plane function on a data center which is closer to the access. So basically, depending on the service that we have to provide, we can have a centralized data center, we can have a local data center, and we can have edge data center. So if we need the very low latency, we will have our user plane to the edge of our access network. Or we can have the user plane at the aggregation layer, but the control plane can remain in a centralized data center. So we have a centralized signaling plane which simplify operation and maintenance. We can have a local data center for traffic localization, and we can have edge data center to improve the user experience and to reduce the latency as low as 1 millisecond on the user plane. And we have the native Mac capability, that is to move application, user plane, and computational capabilities closer to the access network. So actually, the HCIA defines 7 Mac scenarios, which are divided in 3 categories. We have application localization, content regionalization, and edge computing. So basing on the type of service that we have our user plane function, and we have our computing, and we have our storage closer or not with respect to the access network. So for example, we have video optimization. It is at the content regionalization. Enhanced reality is the edge computing, because in this case, we also need low latencies. Enterprise distribution is application localization. IOV, IoT, they are edge computing. Video stream analysis, it is a content regionalization. And sensitive calculation, they are edge computing. With edge computing, we also increase the security, because when we have, for example, sensitive information, and I'm talking about, for example, an enterprise that manages some sensitive information, if we use Mac, we basically our information don't go to the public internet. They will remain close to the access, at the edge of the access. So it is more secure. So till now, we talked about basically the core network. And just give me 1 second, because I'm not able to clear the drawing. So we talked about the core network architecture, but we also have some changes from the bare network architecture. So on the bare network, which is the first change that we will see. Let us considering this picture. Sorry. Okay. So let us consider this picture. From here, we can see a transport layer. We have layer 2 and layer 3. So let us suppose our user equipment send or receive messages to the G node B, and we are in a non-standalone solution. And our G node B needs to communicate with the 4G connector, the 4G radio side, sorry. So in this case, what happened is that the information reached the layer 2, but NR and LTE cannot communicate directly. So the signal flow is this one. We have to go back to the layer 3 and then again to the layer 2. This is actually time expensive. So since with 5G, we aim to reduce the latency, we have to avoid this kind of communication. So we need to allow 2 nodes to communicate directly each other without going again through layer 3 and then go down again to layer 2. So the first change that we will see is that we need to upgrade our layer 2 to a layer 3. So in this way, so we basically upgrade our switches and in this way, two nodes at layer 2, which is upgraded to a layer 3, can directly communicate each other, being more efficient and less time consuming. So basically we are pushing our layer 3 to the network edge. And another technology that is used at the barrier network is the flexible Ethernet. With flexible Ethernet, we are able to perform hard slicing. Flexible Ethernet can support different MAC rates that may or may not correspond to an Ethernet physical rate. So this means that with flexible Ethernet, we can have flexible connectivity between routers and optical transport equipment independently on the physical interfaces between routers and optical transport network devices. So we can remotely adjust the bandwidth as needed. And flexible Ethernet also uses the TDM. And with these features, we are able to perform basically netto slicing at the transport network. So for the management plane, each fragment has an independent configuration, has an independent management, and it has an independent maintenance. And as I said, each segment resource can be flexibly adjusted as required. We can flexibly adjust the bandwidth. On the control plane, again, in this case, each fragment has an independent control resource and control protocol. And we can dynamically create, modify, and delete fragments. That means basically create, modify, and delete netto slicing at the transport layer, at the barrier network. And on the data plane, what can we do? We can create, we can perform our netto slicing, and we can differentiate services, but also we can differentiate users. Here we have an example. We have three, let's say, hard pipe in which we are going to divide basically our application. So we have one pipe for enhanced mobile broadband, one pipe for ultra reliable low latency communication, and one pipe for massive machine type communication. But we can see from here, inside the pipe of ultra reliable low latency communication, we can make a further differentiation. We have here three different vehicle constructor, which has, for example, BMW and Toyota, and inside the same pipe we can have the soft pipe to differentiate at user layer, at user level. So the flexible Ethernet is the key technology that allows us to accomplish the slicing at the barrier network. So we talked about the core network and we talked about the barrier network. We still have to talk about the wireless network, but I think that now we can have a break of 15 minutes, so we can start again at 11:15, and we can go on with our presentation. I remind you, please, if you have any question, you can write your question on the question and answer window, and then we will collect all of your questions and we will create an FAQ area on the Huawei Talent webpage, so you can find the answer to your question in the website. So we can have 15 minutes of break now, and then we can continue with our presentation.